Okay, Chem students, we're going to do another Chapter 1 topic. These are the resonance rules and resonance structures. A very important concept in organic and biochemistry. So resonance structures are used when a single Lewis structure doesn't work. Okay? A single Lewis structure can't show how the electrons are distributed in a molecule or an ion. We have special arrows that we use, and so you have to follow those conventions. There's arrows between the structures, and there's arrows in the structures that show how the electrons move. The electrons that are moving are always in parallel pi bonds and 2p orbitals. They have to all be parallel to be able to move the electrons around. Delocalizing electrons is always a stabilizing effect because it helps to minimize the electron repulsion. So here are the arrows that we use. Okay. The double-headed arrow like this is drawn between two resonance structures, and that's what it means. This is not equilibrium. That would be two different arrows pointing in opposite directions. So this is a very specific use of this arrow. If you show a full-headed arrow in a structure pointing someplace else, what you're saying is the electrons that are at the start of the arrow are moving to where the arrow is pointing. And again, this is a very specific thing, very specific locations. So you don't want to draw it in a sloppy way. If you use a half-headed arrow, same idea, except one electron is moving instead of two. We won't actually use that right now, but this will become more important in our Chapter 10 topic of free radicals. So let's start off with some rules of resonance. I sort of made these up, so I don't know if they're really rules or not. But I propose that there are four common resonance patterns in organic chemistry. We have donor sites, where the electrons come from, and those could be lone pairs or pi bonds. And we have acceptor sites, which could be empty 2p orbitals on carbon, carbocation sites, or pi bonds. So pi bonds show up in both donor site and an acceptor site. And remember, resonance always uses 2p orbitals. So here's our first pattern right here. Lone pair donation from a 2p orbital into an empty 2p orbital, or of a carbocation or a pi cation. Okay, so I've drawn them this way right here. You'll see I have a carbocation next to a nitrogen lone pair. So that carbocation would like to share those electrons. So we point them in between because they're making a pi bond where the electrons are shared. And that moves the positive charge from the carbon to the nitrogen. Now nitrogen's okay because it still has a full octet. This is actually the better structure. It looks like this should be because carbon's more electropositive, but carbon's missing a bond here, so, and an octet. If we bring those electrons in, we have a full octet and we have an extra bond, which is better. But this is still a valid structure. It's a good structure, informative for telling us how the chemistry occurs. We could do exactly the same thing if we had an oxygen next to the carbocation site. So if I had an OH sitting here, I could bring these electrons in and share them and make a carbon-oxygen pi bond. So remember, both p orbitals on these atoms here. Even though I can't see the p orbital here, it is a carbocation, empty p orbital. Okay, and full octets and extra bond is better, but both are acceptable. This could also occur in an sp situation where we have a triple bond. So the carbon here is drawn without a full octet. We borrow the electrons from the nitrogen, and we end up with a carbon-nitrogen triple bond, and the nitrogen then carries the positive charge because it doesn't have its lone pair anymore. Even oxygen could do this. Oxygen, if it's next to a carbocation, can share its electrons in, and we would have a triple bond with the oxygen and a positive charge on the oxygen. This again would be better because we have full octets and an extra bond. This actually has a special name called an acylium ion that we study later on in carbonyl chemistry. Even fluorine can do this. So if we had a carbocation site next to fluorine, which has a lone pair, we can borrow that lone pair in. The positive charge moves to the fluorine, which is still a good resonance structure because we have a full octet and an extra bond. But remember, fluorine is the least willing to share. Okay, and then oxygen. And then nitrogen. Nitrogen's much more willing to share because it's less electronegative. So this is kind of the same thing in reverse, except now I'm starting with neutral polar pi bonds. So we would normally write a structure like this. Say if this was a ketone, we would write it like this. But what I'm doing is I'm showing the electrons moving to the oxygen. I'm not changing any atom. I'm not changing any orbitals. But I would write it like this. In the previous slide, it was a cation. We had an extra bond here, okay, that we don't have here. This is just a neutral, stable pi system, polar pi system. And so, while this is not as good, it is acceptable. It's an okay structure. In this case, I showed the 3D structure, so you can see how this works. Got a p orbital here, and a p orbital here. And all I'm doing is shifting the electrons over to this p orbital. They're still parallel here. Okay, I have all three pairs of electrons here, so I'd have a minus formal charge and a plus formal charge on the carbon. I could do something very similar with an imine, so I have a carbon-nitrogen double bond instead of a carbon-oxygen double bond. But again, nitrogen's more electronegative, so I shift them over. So now I have the minus on the nitrogen, positive on the carbon, so this is an okay structure. The pi bond looks pretty much the same as it did up here, okay? And then I'm just shifting the electrons over, not changing a single atom or orbital, just the electrons. And so I have a minus charge and a plus charge, whereas this was neutral. I could even do this with a triple bond. I have two pi bonds, so if I take one of those pi bonds and shift it over to the nitrogen, I would make a minus charge on the nitrogen and a plus on the carbon. That reinforces the natural polarity that's there. So this is the better structure because I have full octets and full bonds. But this is a valid structure, helps us understand the chemistry. The triple bond will have one pi bond perpendicular to the other pi bond. Okay, we can only move one pi bond over, we move that over, and we have the minus formal charge on the nitrogen and the plus formal charge on the carbon. Okay, so these are all Lewis resonance structures where we can redistribute the pi electrons to different places. Okay, so our second pattern is kind of it's a hard one to see, I think, for beginning students. We're going to look at a lone pair, so it has to be some atom that could have a lone pair. Certainly fluorine, nitrogen, oxygen could. Even carbon could have a lone pair if it was a minus charge. Okay, so anytime we have a minus charge and it's next to a pi bond, we can take that lone pair, if it's in a p orbital, shift it in and make a pi bond there, but that would force us to move the pi electrons over to the far distant atom, X in this particular case. Now it turns out I wrote XYZ because we can put just about any carbon in organic that you want in there. Certainly carbon, nitrogen, oxygen are very common in this kind of a situation. I tried to show over here in 3 dimensions how that would look. Okay, this has to be a p orbital, and that's what you can't see when you're a beginning student. You can't see that this is a p orbital and can share into this pi bond. Okay, and then you have parallel overlap for the new pi bond here, and the lone pair is on the X, also in a p orbital, which is very hard to see in this structure here. Okay, so that requires a little experience, and drawing these structures will help you get that. So many ways. I have a few of them down here. I could have a nitrogen close to a carbon-oxygen double bond. This would be an amide linkage. So the nitrogen donates its electrons, allows oxygen to get more of that electron density, which it certainly wants. It's the most electronegative atom that we commonly use in organic chemistry. And in fact, if you look in, this is a common linkage in proteins between the amino acids. And if you look at a biochem book, they're going to tell you that this second structure is about 40% of the actual distribution of the electrons. So maybe this is about 60%. So even though it doesn't look quite as good, because we have charge separated, it's a very significant part of the picture. Okay, if we come down here, the nitrogen could donate into a carbon-carbon pi bond. Probably not as strong because I don't have an oxygen sitting over here, but still a valid structure. This structure right here is called an enamine, and it actually reacts in its chemistry from the carbon here very often instead of the nitrogen as it looks like it would here. So this is a very useful structure for understanding the chemistry, but again, very hard to see. Lone pair next to a pi bond. Okay, this is a funny looking group, 3 nitrogens in a row. We call that an azido group, and it has different resonance forms. All the nitrogens are together take the lone pair, in this structure here, take the lone pair, push it into one of the pi bonds of the triple bond. The other one's perpendicular. And then that would give us a new distribution with the minus at this far end instead of at the first nitrogen. The nitrogen in the middle is always sharing on either side with the 4 bonds. So triple bond here, single, double bond, double bond. So it's always going to be a plus charge in the middle. Okay, in a azido group, we'll talk about that in chapter 9. If we have a minus charge, say on an oxygen, that's a good place to put a minus, but it's even better if you have a carbonyl next to it. We can push in and put the minus on both oxygens. Very stable for this, this anion. We could do the same thing if we had a carbon-carbon bond. We could push the oxygen lone pair in with the minus charge to the carbon here. Now this isn't going to be quite as good as above because one of them's a carbon and one of them's an oxygen. But still, this is very important chemistry. This is called an enolate, and this kind of structure is useful in biochemistry to help build up more complicated structures because reactions can occur from the carbon here, as this resonance structure shows us. Okay, this is a structure where I have 2 nitrogens in a triple bond bonded to a carbon here with a lone pair. So this is a diazo group, and I can take the lone pair and push over to the nitrogen into one of the pi bonds. The center nitrogen still has 4 bonds, and you can notice in both resonance structures. But now the minus is on a nitrogen, so this is actually a better resonance structure than the first one because of where the minus is on the more electronegative atom, the nitrogen. Now in this case, I actually take the minus charge and push it into a pi bond that is part of a ring full of pi bonds. We call this kind of a ring where the pi bonds alternate double, single, double, single, double, single. We call this an aromatic ring, and they are very, very stable, very exceptional chemistry. They're usually in their own chapter. They're not considered to be alkenes. But I can do the same thing multiple times that I did above once. I can push these electrons in and push them over to this carbon. Okay? But you'll notice when I get to this carbon, I have another pi bond right here. So I could push these electrons in and push them to the next carbon here. And you'll notice when I get there, I have the electrons next to another pi bond, so I can push them in to make a pi bond and push them over here. So all these lone pairs that you're looking at, here, here, and here, are really p orbitals. Okay? It's harder to tell on the oxygen here. One of them is a p orbital, but the other 2 are sp2 orbitals. So if we come down and draw a 3D structure, you can see this a little better. So this has to be a p orbital to be parallel to the pi bond. So notice how all these lines are parallel to each other. They're not tilted. So these electrons are pushed in because we have a place to push these electrons here, at this position here. But these are next to this pi bond. We push in and over here. We push in and over here. And so with the 3D structures, you can see how this actually works. Okay. Now this turns out to be kind of a good thing. When it happens, it can make certain reactions work better. And these 3 reactions that I show here, basically I'm having some sort of base pick up the proton and leave the electrons behind on the oxygen. And I'm doing that same reaction in all 3 cases. But you'll notice on the top, when I pull off this H, I leave the minus next to the aromatic ring. And so I can go around this ring and put the minus at 3 positions inside the ring in addition to the oxygen, just like we did up here. Okay. Now, this ring has a little bit of that. It has 1 pi bond, but these are sp3 carbons here. I don't have any p orbital on an sp3 carbon, so there is no resonance. I can push in and take that proton off, and then I could spread the electrons out 1 time to this carbon here. So that still looks okay. I'm spreading the electrons out. Or I might have a ring that looks just like those above except no pi bonds. So I could still take off that proton and leave the minus on the oxygen. So not too bad, but I cannot push in here because I actually have a hydrogen sitting there. That's an sp3 carbon. And so when you look at this, this one definitely looks better. And this looks second best, and this looks third best. And if you look at the energy it takes to do each of these reactions, the top one cost us about 14 kilocalories. What I often suggest to my students is to consider each little calorie as $1. And so if we had 14 kilocalories, okay, you come down here and look at that, that would be like $14,000. So this reaction is going to cost us. This doesn't happen spontaneously. We have to do a little work to get over to this side. So we take this this proton off and we go uphill 14 kilocalories. In this case, we go up a little higher because it's a little harder to form this anion since it only delocalizes into one carbon. So that costs us about 17 kilocalories, or we might say $17,000. In the last case, it cost us 22 kilocalories, or we might say $22,000, to make each of these guys. So you can see the first one is much more probable and easy than the second one, which is more probable or easy than the third one. But even the third one's possible if you have a good enough base. Okay, resonance pattern 3 is where we have carbocations. So we have a carbocation that's missing electrons. Remember, the empty orbital is a p orbital. If I have a pi bond that can donate into that, I can help that carbon out. The only kinds of pi bonds that we will take electrons from in this situation are carbon-carbon pi bonds. And so we have three possibilities. We have a carbon-carbon alkene that can donate over, and you'll notice the positive charge moves to the other end, and the pi bond is here. So this is very good resonance, and I tried to show that here with the 3D structures. So again, notice how the p orbitals are all parallel to each other. But that's also true of a carbon-carbon triple bond, which has an alkyne linkage. One of those pi bonds will be parallel to this p orbital. So we can move those electrons over and leave a little hole here, this carbocation, and make the pi bond on this side. The other pi bond doesn't change. Notice how it's perpendicular, okay? And then we could even do that from an aromatic ring. So you remember the aromatic rings above were accepting electrons, but now we have an electron deficient site next to the ring. The aromatic ring is going to donate its electrons to help out. So if I take these electrons and move it over, this little part of the molecule right here is basically what we're doing up here. Okay, it's the same thing. But once I get here, because of all the pi bonds in the ring, I could do that again. So I could move these electrons over, have the positive charge in this position. And there's another pi bond, I could move it over and have the positive charge in this position. So if I have an aromatic ring, I can put that positive charge on 4 different centers. And that's going to help make it easier to form, make it a little more stable. Now down here, notice how all the p orbitals are parallel. Okay? In every single structure, I don't change any atom, I don't change any orbital. All I change are the pi electrons, moving them here, moving them here, and moving them here. Okay, so that's an important idea. A lot of times I see students draw the p orbitals at all different sorts of angles to each other. This only works because all the p orbitals are parallel. Okay, so our fourth resonance pattern is sort of really a combination of other ones. But I show here a polar pi bond, and I have a pi bond next to it. Since I'm donating these electrons, I want this to be probably a carbon-carbon pi bond, like an alkene or an alkyne or an aromatic like we showed just above. But I could take these and move them both at the same time. So I could move these electrons to the oxygen at the same time as I take these electrons from the carbon-carbon pi bond. And that will leave sort of a little hole here, positive charge, and give the oxygen a little bit of extra electron density, minus charge. So we have charge density. We have one fewer bonds. So remember, that's going to make it not quite as good. We have charge separation and less bonding and incomplete octet. Now, if I wanted, I could come back, since I have a positive charge next to this pi bond, and donate these electrons in. Okay, and then I would just have the normal old carbonyl resonance that I showed up in the first part. Now, I could have done that stepwise. I could have taken these here and then brought these over. So that's another way to do it. But I'm just trying to show how a pi bond can donate into a pi bond. All right, and then here would be the 3D structures. So first I'm saying we take these electrons and move them to the oxygen, away from this carbon right here. And then we're going to give them back, and then have the positive charge on the carbon next to the oxygen. This could also be done with a triple bond. So if I have a nitrile down here, I could take the electrons and move them in between from the alkene, and then give the electrons to the nitrogen. So I would have charge separation. I would have a fewer number of bonds, one fewer bonds. I could come back in with these electrons and give them back to this carbon here, and then have the positive charge next to the nitrile, nitrogen. Okay, and again, here's the three-dimensional form that we're looking at. I use two arrows to show them move all together, and then I come back and bring them back in here. This could have also been done stepwise. I could have taken them here and made this structure, and then brought these electrons in here to make this structure. So either way is acceptable. I'm just trying to show different possibilities. Okay, so these are just a sort of a hodgepodge of other possibilities. This is a neutral aromatic ring called benzene, and what I want to show here is how the structure is always neutral. I don't make any charge. If I just shift all the excuse me, if I just shift all the electrons over one position, I get something that looks almost the same. It's certainly equivalent, but it's not identical because up here I have a single bond at this position, and here I have a double bond. But this is very good when you can make equal resonance structures. Okay, it's 50-50. Now here is what we did before. We took the electrons to the nitrogen because it was more electronegative. That gives us a charged resonance structure, but still informative. It's helpful. Here's the same thing with the nitrile. Okay, remember these empty orbitals are p orbitals. So even though I can tell there's two pi bonds here and two p orbitals on the carbon, not as easy to see here and not as easy to see here. Okay, so one of these lone pairs is a p orbital and the empty orbital is a p orbital. Here's a simple carbonyl of an aldehyde, same idea. Here's a simple carbonyl of a ketone, same idea. You can see how this idea repeats itself. Many functional groups in organic chemistry have a C double bond O. We'll see a few more right here. Okay. The neutral ones are the best, and these are okay. So here's several more carbonyls. Here's a C double bond O with an NH2. So this is an amide with an OH. This is an acid with an OR. This is an ester with an F here. This is an acid fluoride. Okay. I can take the electrons to the oxygen because that's consistent with our idea of electronegativity. Okay, not as good because I separated charge and I took away a bond, but still very informative. The nitrogen can bring its electrons in now because it's next to the empty orbital, and that would give us back our bond, but we still have charge separation. Okay, and I can do that with all of these other groups. So the first one gives us a carbocation, but the adjacent atom with the lone pair can share and gives us back that bond, although it moves the positive charge to that atom. So here are the positive charges on nitrogen or oxygen or fluorine. Okay? So now if we tried to classify these in order, is A, B, or C better? Okay, so you could think about it a bit. What do you think? What's going to be the order for these guys? I have some possibilities over here. You could stop and make your guess and then check. Okay, so when we look at it, we see this has the maximum number of bonds and no charge separation. So it looks like A would be the best here. Okay, so that's either D or A here. So then the choice is between B and C. So B looks pretty good because it's got the positive on carbon. But remember our rule, more bonds and full octets is best. If the nitrogen loans its own pair, we have an extra bond and we have full octets. So actually C follows A, and B would be in third place. So we need A, C, B in terms of the order of goodness for all of these. Okay, they would all have that same direction. So here's best, second best, and third best. Okay, so in resonance, more bonds is always better than being consistent with charge or electronegativity. When the number of bonds are equal, then it's better to be consistent in your charge. So negative on more electronegative atoms, positive on more electropositive atoms. Okay. And then finally, neutral is better than charges. So if you can use something with a neutral structure, that's better than having charge. Okay, so I have here now just a couple little examples to work through. Here's a condensed formula, so we want to write that out. When we wrote it out, we'd count up all the electrons. First we need a 2D connection. Then we have to add in electrons to the more electronegative atoms first. Okay, and so I have some questions up here. What's the formal charge on all the different atoms? What is the best resonance structure? And what is the hybridization of each atom? These are all sort of tricky a little bit. So first let's make our connection, our 2D connection, and I actually added in the electrons too. Okay, now I came up a little short on the carbon here. So if we were writing formal charge, we would have to put a formal charge on this guy. Hopefully you know what that is. Fluorine looks okay, nitrogen looks okay, but the oxygen, we'd have to write some formal charge there. So I'm just pausing to give you an idea to think about. So I see this carbon needs electrons. This has too much electrons, so I'm going to bring the electrons in to make a carbon-oxygen double bond. And then we'll see what other resonance structures are possible. Because remember, I could borrow from the nitrogen lone pair, or I could borrow from the fluorine lone pair. I'm just borrowing from the oxygen because that looks like the best possibility first. Okay, so let's take a look. I borrow these in. I have my plus and minus formal charge. No more do I have formal charge. So this is going to be our best structure. We have an extra bond, no formal charge. Looks pretty good. But I could have borrowed from the nitrogen, so if I do, then I have to push back to the oxygen. That's going to separate charge, but it gives me back that bond. Okay? And then I could have borrowed from the fluorine, but then I got to push back to the nitrogen. So that puts the positive charge on the fluorine. So these are our resonance structures right here. Now the best one is going to be B. And then we have to decide which atom can share its electrons the best. And I think we would all go for the nitrogen sharing the best because it's the least electronegative. And then oxygen, fluorine would be next because fluorine's sharing. And then last place would be where there was no sharing of electrons at all. We had incomplete octet and one fewer bond. So this would be the order that we're talking about. So make sure that looks consistent with what you're thinking. Okay, now let's do kind of the same thing, but notice I put a little plus charge here, and I snuck in a hydrogen right here on the oxygen. So this is going to end up being a pi cation. Okay, so we have kind of the same basic connection, except this time I have an OH. Okay, if I put in the formal charge here, I'd have a plus. And I could borrow from the oxygen lone pair, the fluorine lone pair, or the nitrogen lone pair. And so here's the way I borrowed them. Nitrogen first, then oxygen, then fluorine. Okay? So here would be our structure with incomplete octet and fewer bonds. Share with the nitrogen, full octets, extra bond. If I share with the oxygen, I have to push them back to the nitrogen. Okay? And if I share with the fluorine, I have to push them back to the oxygen. In each case, I would put the positive charge on that particular atom that shared. So here was on the nitrogen, here's on the oxygen, and here's on the fluorine. So the best resonance structure would have the more bonds, and since we got a plus, we're going to put it on the least electronegative atom. That would be nitrogen, followed by oxygen, followed by fluorine, followed by the structure that does not have enough electrons on the carbon. Okay, so we would get an order something like this, B, C, D, better than A. Okay, just a few more examples and then we'll be done. Okay, I have two structures here. How do we get over to the other side? I see a lone pair next to a pi bond. At the end I see an electronegative atom. That would be good. So if I could take these electrons and move them in to the pi system, I would move these on. Now you might ask yourself, what kind of a carbon is this? Hybridization. And a lot of people say it's sp3, but it's not, and you can see that in the next structure here. Okay, so but you would have to see that to draw the structure, and that's what's kind of hard for a beginning student. So if we bring these in and move these over, it's easy to tell that this is sp2. However, it became hard to tell that the nitrogen is sp. Okay, that's easy to tell over here. So in all these resonance structures, you want to find the resonance structure where an atom has its most bonds. In this case, carbon has most bonds here. And then make your judgment of hybridization on that one. For the nitrogen, it has the most bonds here. So we would decide on the nitrogen here. And if we do that, we'll get the right answer. Okay? So let's see what happens. We push in, the minus moves to the nitrogen. So, this looks like the better resonance structure because minus is on nitrogen. We have the same number of bonds on both sides. Now in this case, this is a tricky one because boron only has 6 electrons. And so we would like to borrow, we could borrow from any of the fluorines, but I just drew one with the obvious electrons. So I could bring these electrons in between to share. That would give boron a full octet. But remember, it splits these electrons evenly in formal charge, so it would pick up an electron credit and get a minus charge. The fluorine, on the other hand, would lose an electron credit by sharing its electrons and pick up a positive charge. Let's see what that looks like. So that would look something like this. Okay, so again, kind of a hard thing to see what to do with these lone pairs, because these lone pairs, we're not saying they're the same. One of them is in a p orbital that we can see right here, but hard to see right here. Okay, so in this case, it looks like the oxygen's sp2. It would have a plus formal charge, and so it wouldn't be surprising if we took the electrons back to the oxygen and put that plus charge onto the carbon. Okay, so that would be an alternative resonance structure. This is still the better structure because it has more bonds and full octets. That would look something like this. So this is what we call pi cation. Here's our little amide again. So if we go from the neutral structure, we would push the electrons to the oxygen. Well, minus charge on oxygen, plus charge on carbon. Next to the lone pair on nitrogen, we could bring these in, and then that would put the pi bond between the carbon and the nitrogen. So in these structures, the nitrogen hybridization is most clear here. It's sp2. It's sp2 over here too, but hard to see because we're not seeing its donation into the carbonyl. Okay. If we looked at the oxygen here, we might say the oxygen is sp3, but it's really sharing its electrons with the carbon. We can see that easily here, so it's sp2. Okay, so a little bit hard to see, but that's part of learning organic and biochemistry in resonance. So in this one here, I see the fluorine has a plus formal charge. I could bring these electrons back to the fluorine, so I'll take my arrow from the middle and point it to the fluorine. That would leave the positive charge on the carbon right here instead of the fluorine. Okay, so that would look something like this. So you can hopefully assign the formal charge and everything as we go through. And hope this helps you with the resonance a little bit. It is a tricky subject, I think one of the harder things to learn in organic chemistry.